There are two basic types of transistors, NPN and PNP. In this film, we will study the NPN transistor. The name labels the parts. Two large N regions with a thin P region located between them, which is less than 1/1000th of an inch thick. Applying a DC voltage across the transistor will not provide appreciable current flow, regardless of polarity. How can we achieve large current flow through the entire transistor? If we connect the negative terminal of this battery to one of the N regions and the positive terminal to the P region, we have forward bias, which will give us current flow through this part of the transistor. To obtain current flow through the entire transistor, we add this circuit. Since this addition is the opposite of our forward bias arrangement, it is called the reverse bias. In effect, we now have two diodes. The left one operates under a forward bias voltage. The right one operates under a reverse bias voltage. To find out how well this combination of forward and reverse bias voltage works, let's examine their effect on holes and electrons. Let's consider the electrons first. Under the influence of the applied forward bias, electrons from the left N region move towards and across the junction into the P region. The electrons injected into the P region diffuse from a point of high concentration at this junction to a point of low concentration near the depletion region. As soon as they enter the depletion region, the reverse bias voltage goes to work. The electrons now move toward the terminal, out of the transistor, and into the conductor. The combination of forward and reverse bias voltages has resulted in a heavy flow of electrons. Anywhere from 95 to 99% of the electrons flow from the negative terminal at one end to the positive terminal at the other end. The other 1 to 5% combine with existing holes in the P region. We will now show this process of recombination in detail. Watch. For every recombination, a new hole is created by the exit of an electron. The thinner the P region, the fewer the recombinations, and the greater the number of electrons that will reach the second N region. Since the forward biased N region is emitting electrons, it is called the emitter. The reverse biased N region is called the collector. The P region is called the base. Emitter, base, and collector. These are the three basic sections of the transistor. In many respects, the transistor is like a variable resistor. In this circuit, the transistor offers maximum resistance to current flow, and there would be a large voltage across the transistor. But by applying a forward bias voltage, a large current is made to flow through the transistor. A considerable voltage drop can now be measured across the load resistor, confirming that a large current flows through the transistor. Its resistance is reduced. The amount of current flow is increased or decreased by varying the forward bias voltage. The higher this voltage, the more current flow through the transistor. Lower voltage, less current. Forward bias voltages used with transistors will rarely exceed 1 volt. For germanium transistors, the most common range of forward bias voltage will be from 0.3 volt to 0.5 volt. For silicon transistors, the most common range of forward bias voltage will be from 0.8 volt to 1.0 volt. The amount of current flow through the transistor is determined by the forward bias voltage applied to the emitter-to-base circuit. But what about the reverse bias voltage? There are 3 points to remember. The first is that the reverse bias voltage is mainly determined by the value of the collector supply voltage. The second is that this voltage source will vary. It might be 3 volts, it might be 6 volts, or it might be 9 volts. The third and most important point to remember is that decreasing or increasing the collector supply voltage will cause only negligible changes in the amount of current flow. Now let's analyze the transistor's ability to amplify electronic signals. The oscilloscope on the left is reading an AC signal that is being fed into a circuit. The oscilloscope on the right is reading the output of that circuit. As you can see, the signal has been amplified. To see how amplification has been achieved, let's use this circuit. It consists of a transistor, a forward bias voltage circuit, and a collector voltage circuit, including a load resistor. The input signal is fed into the forward bias circuit. Voltmeters have been added to indicate changes in voltage. During the positive alternation of the input signal, the forward bias first increases, then decreases back to normal. As a result, the transistor current first increases, then decreases back to normal. The voltage across the load resistor therefore increases, and then decreases back to normal. But the voltage across the transistor does just the opposite. It first decreases, then increases back to normal. During the negative alternation of the input signal, the forward bias first becomes smaller, then comes back to its original value. This in turn causes the collector current to first decrease and then increase again. The voltage across the load resistor again follows the current changes. First a decrease, then back to normal. But the output voltage first increases, then drops back to normal. Now watch the complete action. If we pick up the output signal at these points, it would look like this on an oscilloscope. The signal we fed into the circuit is now amplified many times. Note, too, that it is 180 degrees out of phase with the input. Amplification is achieved by having the low voltage or forward bias circuit control the output of the high voltage or reverse bias circuit. To explain amplification numerically, let's assume the forward bias voltage is 0.3 volt and that the input signal is 0.2 volt peak to peak. During the positive alternation, the total forward bias voltage increases from 0.3 volt to a maximum of 0.4 volt, and then decreases again to 0.3 volt. During the negative alternation of the input signal, the total forward bias decreases from 0.3 volt to a minimum of 0.2 volt, and then increases again to 0.3 volt. In the low voltage circuit, we have a 0.2 volt change in voltage. That is, the difference between the maximum 0.4 volt and the minimum 0.2 volt, which is causing a far greater change in the high voltage circuit. In this typical circuit, the change is 4 volts. Thus, a 4 volt change at the output has been caused by a 0.2 volt change in the input circuit. Amplification is equal to the output divided by the input. In this case, 4 volts divided by 0.2 volt gives us an amplification of 20. Other amplification factors are possible with different transistors in different circuits. However, the principles of amplification remain the same. In a schematic, the NPN transistor is represented by this symbol. It is a simplified picture of the transistor's 3 main elements: the emitter, the base, and the collector. The structure of the symbol makes the 3 elements readily identifiable. Only one of the 3 elements is connected directly to the other 2, that is, the base. The emitter is identified by the small arrow. Note that the arrow on the emitter is pointed away from the base. This symbol represents an NPN transistor. The NPN symbol can be identified by remembering that the arrow is not pointed in. Many transistors operate with forward bias voltages of 1 volt or less. Generally, the value is between 0.3 and 1 volt, but the usual dry cell has a voltage of about 1.5 volt. Assume that we have a transistor that needs 0.3 volt forward bias. This is in excess of what we can safely use unless we employ a voltage divider network. This voltage divider network consists of 2 resistances in series. The first is the internal base to emitter resistance. It is usually less than 1,000 ohms. The desired 0.3 volt is dropped across the internal resistance. The external resistor must drop the balance. In our case, 1.2 volts. This is 4 times the drop across the internal resistance. The value of the external resistor must therefore be 4,000 ohms. In addition to dropping the excess voltage, the resistor we have added also limits the amount of current flow in the base circuit. Therefore, it is generally called a base current limiting resistor. Because the value of this resistor can be changed to drop whatever the excess of voltage happens to be, the source voltage can be more than the 1.5 volts we've used so far. In fact, there's no reason why we shouldn't be able to eliminate one battery completely. We can utilize this battery in series with a load resistor to obtain the necessary collector-emitter potentials, and by adding a base current limiting resistor in series with the emitter-to-base resistance, we can obtain the correct forward bias voltage from the same battery. We can further simplify this schematic. Note that there is no circuit element located between the emitter and the negative terminal of the battery. Therefore, instead of showing a line interconnecting points of the same potential, we can use the circuit symbol for ground. The circuit is complete again when both the emitter and the negative battery terminal are grounded. This is a basic transistor circuit, and this is the signal we wish to amplify. A coupling capacitor is one way of applying this signal to the transistor circuit. The output signal is available between the collector and ground. It is a sine wave, 180 degrees out of phase with the input. A second method of applying an input signal is via a transformer. Note that the secondary of the transformer is placed in series with a base current limiting resistor. A capacitor ensures that no signal voltage is developed across the base limiting resistor, but instead is directly applied between base and emitter. An input signal is applied to the transformer primary. Between collector and ground, the output signal is present, 180 degrees out of phase with the input. There are three basic configurations or circuits used with transistors. They are the common emitter, common base, and common collector circuits. Let's examine this circuit and see which it happens to be. This is the output circuit, and this is the input circuit. Note that as far as the transistor is concerned, only the emitter is common to both input and output circuits. To simplify the picture, we'll eliminate the various other components which we know are part of the circuit. Note that of the three elements of the transistor, only the emitter is common to both the input and output circuits. This is a common emitter circuit. The common emitter circuit is the one most seen in transistor circuits, just as the common cathode circuit is the one most seen in vacuum tube circuits. One important thing to remember about the common emitter circuit is that it provides an amplified signal that is 180 degrees out of phase with the input signal. When the base is common to both input and output circuits, we have a common base circuit. Forward bias requires the base to be positive with respect to the emitter. Current flow in the common base circuit would look like this. The arrows represent the emitter, collector, and base currents, when only the forward and reverse bias voltages are applied. But what happens when the input signal applies its positive alternation? This positive alternation opposes the forward bias. This causes the currents first to decrease, after which they come back to normal. As a result, the output voltage rises first, then falls back, completing the positive alternation. During the negative input alternation, emitter current and therefore collector current first increase, then come back to normal again. This in turn causes the output voltage to decrease, after which it returns to normal. The common base circuit provides an amplified signal in phase with the input. The third basic configuration is the common collector circuit. It is sometimes referred to as the emitter follower circuit because it operates like the cathode follower vacuum tube circuit. To explain the operation of the common collector circuit, let's start with the common emitter circuit and rearrange it. The input is applied to the base circuit. The output is taken from the collector circuit. To obtain a common collector circuit, we remove the load resistor. Place a resistor in the emitter lead and place the collector at signal ground potential. The input signal is between base and collector. The output is across the load resistor. An input signal causes variations in forward bias. The resultant base current and emitter current variations are in step with the forward bias variations. The voltage variations developed across the emitter resistor are therefore also in step with the changes in the forward bias. Note that the output signal is in phase with the input signal and that there is no voltage amplification. Because emitter current variations are many times larger than base current variations, there is current and power amplification. Remember these three applications of NPN transistors. The common emitter circuit provides an amplified signal 180 degrees out of phase with the input. The common base circuit provides an amplified output signal in phase with the input. The common collector circuit provides an in-phase output signal. Current and power amplification is obtained, but there is no voltage amplification. The NPN transistor and its companion PNP transistor is replacing the vacuum tube more and more in modern electronic equipment. Therefore, every electronic repairman should be familiar with their characteristics, capabilities, limitations, and applications.